All right, so yeah, let me just introduce you guys. This is the Eurace Unibi model team. I guess you guys are actually from a few German universities, Bielefeld, Darmstadt, and Lucid Minds. Yeah, just this is interesting stuff for a lot of teams that care about modeling humans, which is a lot of alphabets use cases. So we'd love to hear what you guys have to say. Thank you very much for joining us.
Okay, well, thank you very much for having us. Yes, my name is Herbert Dawid. I'm going to present the stuff, but this is all joint work with Philip Harting sitting here and Sander van der Hoek sitting on the other side, and Michael Neugaard, he's also here on the call from Darmstadt. Okay, so I'm going to talk a little bit first about general agent-based approach to economic modeling, pointing out a few differences between this approach and the more traditional, one could say, neoclassical approach to economic modeling. Then I'm going to talk a little bit about our model. It's a very large model, so I can really just scratch the surface and give a few glimpses. Then talk a little bit about empirical validation, so how the model is able to reproduce several stylized facts that we find in the data. Give you one very brief example of a policy analysis that we did using the model, and then the very quick conclusions, and also talk a little bit about other models that are also in a similar domain. So my plan was overall to talk for about 40 minutes, but if there are any questions in between, please do that. As in particular, if you need some clarification of something, just let me know right away. Okay, so agent-based approach to economic modeling. Well, clearly economic systems are rather complex systems, like many other systems we know. So here we've just put some examples: traffic systems, beehives, human body. And many of those complex systems have properties that are also at the core of what we try to capture in our models, which is the interplay of local interaction effects that have to be aggregated to understand what's going on a more aggregate level. And that's true, I think, for all these examples, and it's also true in particular for economic systems. If we think about economic systems, I would call them very complex systems. And this has different reasons. First, and I will come back to this, of course, the individual particles, if you want, which are making up the system, are as such already very hard to predict because we are talking about individual behavior, and we have to get a grip on modeling this. But just apart from this, here I put a few reasons why those economic models need to deal with a lot of dimensions of complexity, I would say. So on the lower right, you can see that's just a standard graph of firm size distribution. This is actually from Spanish data, but it doesn't really matter. The point here is really that you have firms of very different size, very different properties. And if you want to analyze, for example, industrial dynamics, it's kind of important to be able to capture this, because that, of course, will also influence the behavior of those firms. On the other hand, those individual firms are interacting in rather complex manners. So on the upper right, you can see a bank firm network. That's actually from data from Mexico. No, sorry, Brasilia. Brazil, I should say. So here you can see connections between firms and banks. The blue dots are the banks, the others are the firms. The colors in this graph indicate the different sectors, and you can just see this interaction is going on in an extremely complex network that's obviously also evolving over time. So you have a lot of interactions in rather complex ways of heterogeneous individual actors on the micro level. And this is all embedded in a macro environment, and that you can see on the left. So this is a map of Germany, and in this map of Germany you can see the average income of households in different regions. And you can, so they color code, the darker it is, the higher is the income actually. So clearly here there are also kind of more macro differences. In different regions you have different income levels, which means you have different behavior of households, you have maybe different opportunities for firms, and so on. So there is a lot of heterogeneity to be captured. And in our models, we try to do this. And when we start modeling, of course, the first question might be, so what do we actually want to do with these models? And I should say that in our main goal when building our model of the economy or of different parts of the economy is really explanation, understanding, rather than short-term prediction. And we believe that that's very important. Short-term prediction, of course, can be done, for example, by statistical or also more modern data science methods. But in particular, if you want to do policy analysis, it seems to us that it's very important to have a model that provides you really with an understanding of the mechanisms. So one illustrating example of how important it is to understand how a system might react to some changes in the design of the system is what is called the Cobra effect. Maybe some of you know it. So that is a story from India. When the British were still ruling India, they were somehow concerned about the number of cobras in India. So they started a program where people were paid to deliver dead cobras. And so, of course, the prediction based on a kind of a straightforward, more or less naive expectation of what's going to happen was, well, if people are paid to deliver those cobras, more cobras will be delivered, so there will be fewer cobras in the country. What happened is exactly the opposite. So people started breeding actually those cobras in order to be able to deliver them. And so the original effect was already not what the British had really hoped for. And when they stopped the program, which they did, the result was even worse, because then people who had bred those cobras just let them loose and you had way more cobras. So the kind of the message of this story is you really have to understand how the individual works and how the individual will react to changes in the environment. And to do that, you need kind of a model that is trying to capture this. And that's what we are trying to do. So given that, then the main question is, if you think about building such a model, how much of the complexity do you really want to put into the model? Obviously, it's impossible to put all the different dimensions I was mentioning into such a model. So one really has to be very careful in trying to understand which dimensions are really crucial to understand the mechanisms you want to analyze. So this concerns the type of agents that you want to put into the model. In a standard economic model, we have firms, households, banks, maybe some other actors like the central bank or the government. Which properties should characterize these different type of agents? So if you think about households are consumers, they are workers, so you might want to put some information about their preferences, but also some information about their skills, which will determine how they can do on the labor market. And again, it's really a hard problem to select which properties you want to put. And markets in these models are typically captured in a rather explicit way as far as the protocols that govern the exchange go. So other than more standard economic models, of which I will talk a little bit in a minute, in our models, we really try to have explicit rules and protocols for exchanges on markets, also on off-market transactions. And the last point maybe is the most tricky one, which is how do agents determine their actions. So you need to have a rather systematic approach to determine how individuals choose what to do. So if we try to provide answers to all these questions, we can compare the approach that we are following, the agent-based approach, which sometimes is also called complexity economics, to more traditional standard neoclassical approaches, where people have chosen, and there are obviously good reasons to do that, to reduce this complexity in a very strong way. So the developing models where you have typically very few agents, or the other extreme is you have a continuum of agents, but in both cases the individual agent matters much less. Those models often have much less heterogeneity than we are able to capture in a simulation-based model. So in our models, these dimensions of heterogeneity typically cover different characteristics. Concerning behavior, the standard approach in dynamic equilibrium models is that everyone is optimizing some dynamic optimization or some dynamic objective function. So the really underlying conceptual framework is one of dynamic optimization, which is possible only if you have a relatively simple model in the first place, and second, seems to be at odds with a lot of empirical evidence. So what the agent-based approach rather tries to do is to develop models where individuals act based on adaptive heuristics. And then the crucial question is, okay, how do you come up with a good foundation for the heuristics you want to put into your model? Similar for expectations, standard economic models often assume that the individual who is acting in the model actually perfectly knows the model and is able to predict what the dynamics of the models of the economy as such will be, which is a very strong assumption. Our approach is rather to have what we call locally constructive expectations, where individuals really act more like someone who is maybe an econometrician or something similar. So you're collecting data. Based on this data, you're using standard algorithms to make predictions about the future dynamics of the model. As far as interaction goes, as I said, in our approach, we really explicitly model what kind of institutional framework we have on different markets, whether they are labor markets or maybe energy markets or similar. So we don't use the standard assumption that is often used in economics, which is just market clearing, meaning that without any frictions, supply would equal demand. So that's an assumption we typically don't make in our types of models, but we also take into account that there might be something like rationing and frictions on both market sides. If we want to aggregate, so one of the big questions in macroeconomic modeling is, once you've understood what the individual households, the individual firms do, how do you come from this individual level to the macro level? So how do you, from this, get predictions about what is the average growth rate and similar more aggregate indicators? And in the standard economic approach, this is often done by using what is called a representative agent. So then you have one agent representing the whole sector or all the households. In an agent-based approach, we don't do that, but we rather do what a normal statistical office would do in the real world, which means you take the data from all the individual firms, all the individual households, and you calculate things like GDP in the standard way it is done in a statistical office. Our models are simulation models, so we can run them and we can look at the effects of, for example, policies on different time horizons. We often observe in these models that we have emerging effects, so that there is things like path dependency. So what happens in the short run might actually have strong impacts also in the long run. Which is something that's very hard to capture in a standard equilibrium model, because there you typically can only look at the very long run. And in terms of policy, as I will try to illustrate later, this approach that we are using really So you can capture really details of how the policy works, and that then also might be very useful for policymakers because it might relate to their main problem, which is really coming down to the detailed design of policies.
This may be a good slide to ask this kind of basic questions. The impression that comes across here is that it's a difference of assumptions, where neoclassical assumes that people are more or less rational and far-sighted, and there's a few different categories of people, and most of the dynamics happen between categories, not within a category. Is that about right?
That's about right. So this is clearly a distinction between the approaches, but even more so, in order to be able to be rational. So the question is, what does rationality mean? So you can be rational, so to speak, as a normal firm would be in a very complex economic environment. Those firms all try to be as rational as possible, meaning they try to collect the data and then they make predictions and act based on these predictions. What those firms typically will not be able to do is to understand the economy as such, and so to speak, knowing the model, understand how the dynamics in the model will evolve. Whereas in the neoclassical, if you are in the dynamic equilibrium world, what you assume is that actors in the model perfectly know the whole model. And therefore, they are able really to fully predict what in this, under all the assumptions that the model has been making, will happen in the future. So that's, I would say, of course, it's in the end, that's what's called perfect rationality in this literature, but it's more than just saying they're rational. It's really assuming that you perfectly understand the whole structure of the economy and the whole dynamics of the economy.
Okay, so let me just try to get a better idea of the kind of what the assumption. It sounds like it's a continuum of assumptions. I mean, you can go on the complexity. You can drop as many assumptions as you want, but like here. I mean, certainly if you have perfect foresight, it allows you to hit equilibrium pretty quickly because everybody agrees. However, if you relax and simply say it's a convex optimization problem and people just act locally selfishly, would that be enough to hit those equilibria?
Not necessarily. So, I mean, this then depends on the economic environment you're actually looking at. So there is a lot of work asking the question very similar to what you were just posing. If you have adaptive individuals, will they eventually reach something which resembles dynamic equilibrium? And that might happen, but it's generally speaking not guaranteed.
All right. So then if you look at behavioral economics, the kind of models of how people actually act, where do they tend to fall right now? Like, what do we know about individual behavior and how far these assumptions are from, more empirical work?
Well, so if you look at experimental work, for example, it has been shown in kind of very simple settings that people deviate from what like a standard game theoretic prediction would be. And that might be due to different reasons, because there might be social norms involved or things like that. But there is I think one very clear evidence, which is about intertemporal behavior. So if people are faced with intertemporal decision problems, then they very fundamentally deviate from what is intertemporally optimal. So it's and that's apparently not a problem of that you might have some other regarding preferences or some other social norms involved, but that seems to be just a problem to understanding how your actions today actually will systematically influence your payoffs in the future. And there is a lot of evidence on that in particular in intertemporal decision problems, the assumption that you are acting intertemporally optimal, even if you kind of understand the problem well, is very strong.
Okay, so then I guess it's going to be a question for future slides, is how do you choose the rules for your more complex models based on any experimental work? Because I mean, seems to be the difficult bit now.
Yes.
Okay,
yes.
Cool. Yeah, but you can go on there. Just in the future, it'd be great to know that.
Okay. With this very brief general discussion of this line of work, let me try to illustrate this using our model. So that's the Eurace Unibi model. So this model has been developed since actually 2006. So originally it came out of a European project, so funded by the European Commission. And the overall agenda is initially it was more a proof of concept thing to develop and what we would say empirically grounded agent-based model that you can use to analyze economic dynamics, but in particular also to evaluate different types of policies in different economic domains. And what is very important for us is we are not interested in generating some kind of a black box here, but we are really interested in generating a tool that allows us to understand the mechanisms that are actually leading to those, let's say, policy effects or also other economic dynamic effects. Okay, to give you a very brief sketch of this model, so if I would go into more detail, I think I would spend maybe 90 minutes just explaining the model. So I decided to be very brief, but if you have questions, please ask. So, okay, in the model we have different types of agents. The basic types are households, then so-called consumption good firms, investment good firms, we have banks, and we have a central bank and the government. Now, of each of these types of agents, we have many, and as I indicated before, they differ with respect to different characteristics. Those agents, they interact with different households, on different markets. So this is all kind of rather close to what the standard macroeconomic model would also capture. So we have the households as workers, they are supplying labor on the labor market. As consumers, they are deciding which consumption goods to buy and at which price to buy them. And then they might have savings, and those savings they can invest in very simple types of assets. On the other hand, consumption good firm, so those are firms that are producing the goods that the consumers buy. And in order to produce, they need labor, but they also need machines. And machines in this economic language are the investment goods, or sometimes called capital goods. So those capital goods are traded on the capital goods market. So we have investment goods firms who are selling those capital goods to the consumption goods firms who are then using them to produce. The consumption goods firms also might need to finance externally, so banks might give them credit, and this is managed through the credit market. Now, in all these markets, we have explicit market protocols. I'm not going to go into the details of how those different markets work. I will, in a minute, go a little bit, just sketch the interaction between the consumption goods firms, the households, and the investment goods firms, and how this is generating kind of mechanisms for the diffusion of new technologies, and how this is determining the speed of technological change in the model. Okay, then there is a government. The government essentially is very minimalistic in our model. It is collecting taxes and it is paying unemployment benefits to the unemployed. And the government is running a balanced budget approach, so they adjust the tax rate in order to keep the budget balanced. And then there is the ECB, which is providing essentially the facilities and liquidity to the banks. Okay, before going a little bit into the economics, let me very briefly talk about the implementation. So this model is implemented in FLAME, so that's called flexible large-scale agent modeling environment, which originally was developed for agent-based simulations in other domains like biology. And the basic particle in this implementation are so-called X machines. So every agent here is an X machine. So this is essentially a machine where you have some input stream, you have some memory, and there are transition functions in this agent determining the transition from one state to the other, and that might also generate in some output. So what could the input be? The input, for example, could be if you're a worker and you're on the labor market, the input could be there is an offer for a job with a certain wage associated, and then there will be some decision rule for this worker determining, okay, am I going to accept this job or not? And then the output would be a message to this potential employer, okay, I accept the job or I don't.
Are these stochastic or deterministic?
Sorry?
Are these deterministic or stochastic?
Can be both. So some of our rules are stochastic. Actually, most of them are stochastic. Some of them are also deterministic. So within each of these agents, within of these X machines, we implement, which is the core of the model in some sense, the decision rules. So technically speaking, this is all implemented in C. And I will come to the way we're doing this in a minute.
What's the? I'm trying to figure out the category of models here that's sufficient to express what you have in mind. So this looks like a mix of Markov models and deterministic finite state automata. Is that about right? Like these phi's are probabilities, or are they?
Yes, they can be. As I said, that can be deterministic or it can be stochastic. So in many instances, we're actually using logic models, and then those will be probabilistic. But there are also instances where we will use deterministic rules.
And when you have output stream, it sounds like you can send a message to multiple destinations. Is that correct?
Yes.
And
so this brings me to the next next slide, which is the communication. So one thing about the flame, which actually is very nice and very neat, is that you're really very clean with respect to the information that is transferred. So all the information that is transferred between any agent in this model is explicitly going through what is called a message board. Like here again, a job market example, you would have the firms posting those vacancies on the message board, and the households can actually read those messages, and you can filter what they can read or they cannot read. And then strictly speaking, when the household is answering to the firm, the household would also send a message to a message board, which is then readable only for this particular firm. So technically speaking, it's all done through this very same concept of having all the communications through message boards, which maybe sounds not such a great thing, but it's actually very important because in many models, also in economics in particular, I would say, if you are not really clear about this, then agents might get information within the framework of the model that actually they shouldn't have, because they have never been explicitly told about it. So in this framework is very clear that no agent can actually directly look, for example, at the state of another agent. So all the communication has to go through those messages.
So now this brings up a bunch of phenomena. I'm actually thinking epidemiology it comes up more commonly. The network becomes very, very important of who meets whom, how does information or disease or whatever get transferred. It seems like here the default is public communication, and if you want any more structure, you have to add more job boards or that kind of thing.
Yes, so it really depends on when you post the message, what kind of label you put on the message, who can read that. And that can be a particular firm, or it can be a group of agents, or things like that. So you can generate a network in this rather easily, but you can also, of course, post just public messages.
Right. And now one thing, looking at your, it was like X machines, I think you called them, how difficult how difficult is it to write differentiable machines? Because I'm thinking one way of optimizing parameter tuning or adjusting these models is if they were differentiable, life becomes extremely easy. But of course, that's extremely difficult to set up. So is that even possible here?
So differentiable, you mean you would run this in continuous time, or?
Oh no, I mean, so think neural net. I mean, all a neural net is it's a function that's differentiable with respect to its parameters and its inputs, so that if
Okay,
you're going
okay,
to
I see,
adjust
I
it,
see.
you can just use the derivative, and that would be fantastic if that could be true here. But I mean, that's hard to set up.
So I mean the rule as such is, of course, in our framework, typically not given as a closed form function. So you have a procedure like if the firm is determining how much to produce, essentially the firm is solving a kind of a newsboy problem and a certain expectation about the demand. And so you in the procedure, also in the heuristic as such, you're collecting the data, then you're trying to solve this newsboy problem, and then that's how you come up with the quantity. So in that sense, we don't have that as a closed form, which also means it's not differentiable in that sense.
That makes sense. I think the only, I mean, in neural net world, you use like something like TensorFlow, where you declare your computation ahead of time, and it could be a lot of things, but those individual operations have to be differentiable. So TensorFlow knows what to do with them. If this is C, so obviously the framework has to be set up from the ground up to do that. But yeah, that makes sense.
Yes. Yeah, so I mean, some things, I guess, for some of our roles that would be possible. For others, I think you would have to change the setup. Yeah. Okay, so much more for the technical part. So just to give a very brief sketch of some of the key model properties. So the model basically is a model with some spatial structure, or you might call it geographical structure. So we have different regions. Those regions are located on a grid. The regions might differ with respect to the distribution of characteristics of agents in those regions. And in the policy example I will talk about a little bit later, this was very important, that we're talking about kind of the interaction between different types of regions. So the agents every agent is located in one of those regions. So there's a very clear environment for each agent. And then additionally, they might be linked through different types of networks. For example, there are these firm bank networks. So the firms have ties to special banks. And also in some of the applications we did, we were introducing social networks where, for example, people were communicating wages and thereby influencing also expectations of others, or also providing referrals for other workers. So we have also done work on that. But for many of our applications, the social networks were not part of the model, so this can be kind of switched on and off. So now coming to the empirical micro foundations of the decision rules, which is a very important aspect. Now we're distinguishing between different types of decisions that different agents make. For the firm decisions, and actually the largest part of the decisions in our model are actually the decisions made by firms, we use something we have been calling the management science approach. So our reasoning essentially is that many of the decisions the firms have to make in our model, which is pricing, quantity decisions, the question whether to enter some market or how much to invest and things like that. Of course, there are decisions that firms are making all the time. And for all of these decisions, there is a really large managerial literature in operations management and similar. And this literature in the management science domain essentially is providing heuristics. So for a while, actually, I was myself also teaching operations management. What you're teaching to the students is typical heuristics that you should use to solve certain types of questions. And so we are actually implementing these types of heuristics in our model. For two reasons. One reason is that clearly those heuristics have been derived from some simplified model of this type of problem. So obviously they are relatively rational decisions in the first place, given the information you have about the environment. And second, because these heuristics first are actually taught to managers in business schools, etc., meaning that it's likely that they influence the decision-making of those managers in the first place, and even more so, there are actually decision support systems who have those types of heuristics implemented in them. So based on this, our argument is that using such heuristics, we should be relatively close to what we would expect firms to do in such situations. So that is our basic conceptual approach to capture firm behavior. For individual behavior, for households, so like consumption behavior of households, we do not rely on experimental literature, but we rather rely on empirical literature. Part of this is in the marketing literature or also in consumer behavior literature, where people have done extensive studies to, as I said, we're using logit models. And in this literature, logit models have been found to be quite suitable to capture actual consumption behavior, and so consumption choices between different types of products, and also the question how price sensitive consumers are in different domains. So again, here we are relying on what we believe are empirical foundations, more in that particular case than theoretical ones.
So how do you validate that? Because there's a bunch of behavioral, a game theory kind of stuff where they do real experiments and they, find adequate descriptions of those games. How do you know which of rules for management science or whatnot or behavioral theory apply in a given scenario?
So the decisions we're looking at here are so for the consumer perspective are relatively non-strategic decisions, I would say. So they decide on how much. So they have an income. They have to decide on how much of this income to save and how much to use for consumption. And there is a lot of empirical literature estimating for different countries, but also different types of households, how much they would save and how much they would spend on consumption. So those there is literature indicating that actually piecewise linear functions are quite good in fitting the data in that respect. So we are using something like that, for example, to capture the saving versus consumption behavior. And then if they have determined how much they want to spend on consumption, they might have to choose between different products offered at different prices. And so here we are looking at, again, not an experimental, because there's not so much experimental stuff on this particular issue, but there is a lot of empirical studies, how people would react to price differences and to different degrees of differentiation between the products. And so we are using this. I should also say that, of course, the model we are using, although it has quite a bit of complexity in it, is still stylized. So we are not able to say our consumption good is a TV set, but it's more generic, which of course makes using estimators or estimations for, let's say, the price sensitivity of consumers a little bit tricky, because they are, of course, very different between industries. So in that sense, we are using those studies, and we are starting to calibrate the model using that. But then we are also, and I will come to that in a minute, we are also then adjusting those parameters in order to be able to reproduce phenomena that we observe on a more macro level.
So then how many parameters does a typical model have?
So that's a tricky question. So one could say how many types of parameters or how many parameters, because I mean the agents are heterogeneous, so each parameter, like the sensitivity to prices and so on, in principle could be different across agents. But if we think about just the type of parameters we have, so I'm looking at Philip, I think it is maybe 80, would be my guess.
Well, so I guess I'm trying to get at, certainly every agent could have a different set of parameters, but you don't actually do that. Or you sample those parameters from distribution, and the distribution's parameters that you tune.
Right.
What's your, like, how many parameters you're actually trying to tune versus, in theory, I don't really care how many in theory could be tuned.
Yes. So, okay, I have a slide a little bit later on where we're actually trying to estimate or calibrate, however you want to call it, eight parameters of the model. And the reasoning for that is that many parameters, I mean, once you have worked with the model a lot, you realize many parameters don't have a lot of impact on the overall dynamics. And there are a few who really are quite crucial. And then we are really trying to targeting those.
All right, cool.
Okay, so before coming to that, before coming to the empirical validation of the model, let me just give a very brief sketch of one particular mechanism that is in the model, also because this mechanism is maybe important to then understand the policy example I'm going to show. So one of the things we have been targeting a lot with this model are issues of diffusion of technologies, mechanisms, how technologies diffuse in an economy, and how this is driving growth, but also how this is influencing inequality in such economies. And so one mechanism that we capture is that new technologies, and new technologies in this case are better machines, if you want. So we call this vintage structures capital. So vintage structures capital means you have different types of capital goods, and they differ with respect to the productivity. So we have, as I said, we have this investment good producer who is selling those machines, those capital goods, and they are selling different types, so those different vintages. The firm then has to decide which of those vintages it wants to buy, and this is in the end determining how new technologies actually influence the total productivity in the economy, because this is influencing how fast good technologies might diffuse. And one important aspect we are capturing, and there's also a lot of empirical work on that one, is that there is complementarity between the quality of the machine and the skills of the workers. So meaning you need sufficiently well-skilled people to work with very high-level technologies. And on the other hand, very high-skilled workers might not be very productive if they're working with relatively low quality of capital goods. So this is captured in the type of production function that we're using in the model. And in addition, we are capturing that, of course, the skills of the workers are not just constant, but they actually adjust over time. In particular, workers acquire specific skills, so that's the ability to work with high-tech machines on the job. So in order to acquire those skills, workers have to be hired by a firm which is actually using such technology, and then they will acquire those skills while they're working with those machines. Second dimension where those workers are heterogeneous is the speed by which they learn those specific skills, which we call general skills. And so our idea is the general skills is a proxy for education, maybe. So if you're very well trained, then you will be faster able to acquire those skills that you need to work with those high technologies. So, and now if a new machine comes on the market, if there is such a new vintage with improved quality, then the question is, how does a firm decide whether it wants to buy those new vintages or not? And So again, sticking to the approach I was just sketching, that those firms are really trying to be rational within the information they have. Those firms are trying to predict how productive those different technologies will be for them, which means they have to take into account how the skills of their own workforce is. So if you have a workforce which is not able to work with this technology, then the technology as such is much less attractive for you than if you have already very high skilled workforce, which will be able to use this technology at its full extent relatively quickly. What that very simple mechanism induces in our model is that we have kind of self-reinforcing mechanisms that firms that have been investing in high technologies have better skilled workers because the workers have been learning on the job, and the fact that they have this high skilled workforce then also makes those firms invest more in the new vintages of the future. So you get really a rather robust differentiation between firms in terms of skills of workers, in terms of quality of the machines they're using, and also then in terms of size. And so this mechanism also is indeed influencing the diffusion of technologies. So one application, for example, which is kind of straightforward, and we can also see in the model, is if you have two regions, and in one region the level of education is much lower than in the other, which in our framework means the general skills of workers are much lower, then the diffusion of technologies will be much, much slower because the firms will have low incentives to actually invest in those high technologies. So that's just one of the mechanisms to give a glimpse. Okay, and I could talk much more about this, but I think we're getting a little bit in time trouble. Okay, so then once you have developed the model, of course, the important part is you need to validate it. And the way we have been validating it is, on the one hand, what is here, this domain expert. So our domain expert, to some extent, is the literature on this managerial decision-making heuristics. But also, of course, on the other hand, ideally, you would then want to talk to actual decision makers in the different domains and include them. But what I mainly want to talk about now is this validations. So once you have developed a model, how do you validate it empirically? And here we are following what is now kind of the standard approach in this literature, which is the reproduction of what is called stylized facts. So stylized facts, a little bit a tricky concept, because there is not a very precise definition what a stylized fact exactly is. Generally speaking, those are patterns that you find in the data of, like if you look at macro data of different countries. So like if you look at data of industrialized countries, you get time series of GDP growth rates that essentially look very similar to what I'm showing here, which is the French one, which is the red line. The black line are the GDP growth rates produced by our model. So this means there is fluctuations, endogenous fluctuations, which in our model, and again, that's a difference to standard equilibrium models, are not produced by some external shocks, but they are produced actually by the interaction of the agent within the model. And you see a certain persistence in those growth rates clearly, but you also see repeating kind of crashes, so where you have negative growth rates, and you can also see, of course, boom phases. And so here I'm just showing a picture, but we have actually compared statistical sub-statistical indicators like autocorrelation structures and so on of the output of our model with what one can find in data. And so here one can find nice ability to reproduce these indicators and the data. Now, this is just a macro level. One of the features that are quite appealing about this approach is that we have a macro, a meso, and a micro level in the model, and we can look at stylized facts at also those different levels of aggregation. So we can look at business cycle properties like this one. We can also look at distributional properties generated by the model. So on the right, there's again the figure I was showing before, which is firm size distribution from Spanish data. On the left is firm size distribution generated by our model, and again you can see that the properties are qualitatively very similar, and also the model is reproducing patterns that you can observe on different markets. Like this is a very kind of well-known pattern on labor markets, the so-called beverage curve, which gives this negative relationship between the number of vacancies and the unemployment rate in the economy. So on the right, that's the actual data from the US. On the left, that's the data that our model produces. So the standard way to kind of establish credibility for the models in the agent-based macroeconomics domain is to do these reproduction exercises for stylized facts. What we have also been doing, or I should say maybe have been starting to do, is a more systematic real calibration of these models, or some people might call it estimation, where we really have a well-defined criterion, which is so we are not using a maximum likelihood approach because likelihood functions are not available for these models, but we're using something similar, which is a so-called Markov information criterion, which is based on discretization of the state space, and then you estimate transition probabilities between those discrete states, and you can estimate them for the data, and then you can compare what you get from your model with that one. And based on this, you can get an objective function for such estimation exercises. And here we have done this, or I mean, this is mainly Sander's work. Sander has done this, as I said, for 8 parameters. So what you can see on the left here, where you see the initial sampling, NOLH, so NOLH stands for nearly orthogonal Latin hypercubes. So that's a special way of sampling in a high-dimensional parameter space. Which should have the property that you capture the variation as well as possible without having to deal with the curse of dimensionality. So in this exercise, the parameter settings are sampled according to this approach. And then for each of those parameter settings, and in this particular exercise, there were actually not many samples. This was a little bit more than 500. Then the model is run. For this, you get the output, and then you use the output that you generate with those sampled points to kind of you might call it interpolate in between. So you try to generate a model response surface where you try to anticipate how this objective function would look in between. And based on this, then you can try to find parameter constellations that are even outside the originally sampled set of parameters, which are as close to the data as possible. And that's what you see on the right. That is highly computationally intensive at this point, but in principle it's feasible for a model like this. And so there's still work on this. But I think this is the next step for empirical validation of these models.
How long does one run take?
So really one model run.
No, it depends a bit on the population size, but so our usual population size is about 8 minutes. So for a reasonable time horizon of 50 years.
And that's single CPU?
Yeah, so we are, that would be on a single core. We are running it, of course, on large clusters.
Oh, that's my if you have
the 8 minutes would be on a single core. Yeah.
Yeah.
All right, so that's not bad. You can do 1 million of these fairly easily on a big computer.
Yeah.
Okay.
But of course, to do this, I mean, those are stochastic models. So in order to do an analysis, you need to write all the whole ensembles of runs for each parameter, essentially. So,
Right, but unlike a climate model, you can run millions. You don't get like warning, which is like climate. Yeah.
Yeah. Okay, so let me then very briefly give an example of a policy analysis that we did. We did actually policy analysis in many different domains, but this is just one of them, where we're looking at what in the European Union is called cohesion policies. So one of the main policy objectives of the European Union is to try to reduce the currently still existing large regional differences with respect to productivity, income, and then also other aspects. And the EU has been running such policies for a very long time, for decades actually, and it's costing a lot of money. A third of the EU budget is spent on these policies. And they do different types of policies for that, and one approach they have is that they try to incentivize firms in these low-tech regions, which are called the so-called target regions, to invest. So they provide subsidies for them to invest, and the idea is that they should invest in technologies that are close to the frontier. There's a lot of empirical work, and the empirical evidence that these cohesion policies are working well is not overwhelming. So this is a rather critical debate about how well this money is actually spent. And so what we try to do is to use our model to understand how one could design maybe these policies a little bit more effectively, or at least to understand what are the crucial aspects of the policy that will make it work better or worse. So to do this, first we were running our model for a multi-regional version of our model without the policy. And again, this is just to show that we even here, although we didn't explicitly target it, we were reproducing stylized facts. Like, so we have different types of regions here. The black line is a high-tech region. The red line is a low-tech region. And on the low-tech region, we can have less flexible and more flexible labor markets. And on the left is the output, and that's maybe to be expected. The high-tech region has a much higher per capita output than the low-tech regions, and the low-tech region with the inflexible labor market has a little bit of a higher output here than the one with the flexible labor market. But what is quite interesting is that in our model we can also look at inequality, which is typically measured by a Gini coefficient. And we do get in our model that the high-tech region not only has much higher output, but also much lower inequality. And among the low-tech regions, the one with the inflexible labor market actually has a higher degree of inequality than the one with the flexible labor market, which exactly is not completely obvious, but it fits the data. So if you look at the data of European countries, that's exactly the order you get. So that just to show that also this one we can nicely reproduce. And then we were looking at a particular type of technology policy which has the following form. So if you are in this low-tech region, so you are in the target region, and as a firm you want to invest, you will get a subsidy, which is 20%, when buying a new physical capital, so a new machine. And since the idea of the subsidy is to incentivize the firm to buy machines on the frontier, so the best possible machine available, and there is a discussion in the policy literature whether these policies are actually successful in doing that. So whether the firms who get the subsidies indeed then change the choice of their vintages, or whether they just buy whatever they wanted to buy anyhow and just take the subsidy as a nice support. We implemented different policies where we introduced what we call the alpha parameter, which is saying, okay, which fraction of the firms is the policy actually influencing in their technology choice? And this can go from 0 to 30%. And so we're looking at the effect of such a policy if it is able to incentivize 0 firms up to 30% of all the firms that get the subsidy. And so what you can see here are so-called penalized splines. So this is our standard way to analyze the policy effects. So these are kind of nice tools because you can get kind of clear statistically sound confidence bands about dynamic policy effects. And so here you can see the effect of the policy in the region 1, which is the high-tech region, and the region 2, which is the actual target region. And the color code is the black line is you do not incentivize any firm, and up to the blue line, which is you can affect the technology choice of 30% of the firms. And what is very clear from this is that it's really crucial that you're at least able to incentivize a few firms, because the black line essentially shows you have no effect. So if you just pay subsidies to firms, but you are not able to change their choice of technologies, then this will not help these regions to catch up. On the other hand, if you are able to incentivize only 10 or even 20%, then these policies become very effective. So one of the implications that we would draw from this is that taking into account or really paying attention to the fraction of firms that you can influence seems very important for the effectiveness of this policy. We can also look at the effect of the policy on the regional inequality. Here we get a very similar picture that if you just pay subsidies, but you do not influence the firm's decision making, also inequality is pretty much unchanged. But the same policy that will help to catch up in terms of output will also help reducing the inequality in those low-tech regions. That's what one can see on the right here. Okay, and then what is, as I said, important for us is always to understand the underlying mechanisms. So now we know, okay, without incentivizing the firms, this policy doesn't have an effect, but then we want to understand why. Standard economic reasoning would imply that even if you just pay a subsidy without influencing the technology choice, that should help the firms because you're reducing their costs, you're reducing the investment costs. This should make them actually more competitive. And the question is, why doesn't that work? And I think I'm a little bit out of time, so I will not go into the details, but what our analysis here shows is that this really has to do with the interplay between the local labor market in those regions and the global consumption good market that we have in our model. In particular, there is a problem for those firms who want to expand to hire people that are willing to accept their offers if they have been low-tech firms in the past. So, as I said, maybe we'll skip this because it will maybe take too long. So, but what is really important for us is looking at micro-level data in these models allows you really to understand well what's going on and why those policies work or don't work. There's a number of issues that we have been looking at using these models. So this has been about stabilizing effects of different types of policies. Currently, one of our group is looking at the diffusion of low carbon technologies. So looking at a world where you have green and gray technologies, and you try to understand under which circumstances the green technologies might diffuse or not. We have been looking at different kinds of bank regulations and how they affect crashes in the economy. Quite a bit of work has been done with respect to those cohesion policies I was just sketching, and more generally about regional policies and both on the labor market and on the goods market, and how this influences the dynamics in different heterogeneous regions. Okay, so let me very briefly conclude. So yes, this is one of several agent-based macroeconomic models that are out there in the literature. I would say what maybe is distinguishing our model from some of the others is that we have tried to put more emphasis on empirical foundations. I have been talking about the advantages of this type of approach in terms of being able to capture institutional settings and also some details of policy designs. That you can look at the policy effects also on different time horizons, different levels of aggregation. And again, what is really important is that you don't treat those models as black boxes, but you really try to get a clear picture of the mechanisms. Before concluding, let me say that our model has been applied for these different macroeconomic policy questions I was sketching before. There are agent-based models in different domains where people have been using them to understand industrial dynamics. Also, actually, those models partly are very specific. So there are so-called history-friendly models where people try to understand the evolution of one particular industry, like the computer industry and so on. There's a lot of work in finance, understanding certain patterns on financial markets, like volatility clustering or similar phenomena with such models has been very successful. There are models in the domain of urban geographical economics. Now, a lot of work is shifting towards integrating those macroeconomic models with ecological assessments, and then you have integrated assessment models. There are models in labor economics and similar. So I think it's a very versatile tool to be used. And with that, let me thank you for your attention. If you're interested in our model, there's a webpage for it, where you can look at the documentation and also a list of all the papers that we have done using the model. And okay, some of the papers are here. Okay.
Awesome.
Thanks.
Well, yeah, thank you very much. I did want to ask one question, just kind of to get at the hardest part of what this agenda is about. I mean, the big strength of what you're doing is you have a detailed model. So if the model is right, then you can figure out the underlying motivations. And more importantly, you can say that if the modeled entities act like this, then here's my intervention on those modeled entities, because I have a real world analog to model world, phenomenon. But the difficulty is actually making sure that's true. So what steps can you take to make sure that if the model behaves like whatever, that there is a real world analog to that model behavior, especially when you have parameters and you can tune them to minimize error, and you kind of deviate from the original formulation of the model. Like, how do you make sure it actually hooks up to the real world? Seems like
right. Yeah, well, that's clearly, in some sense, that's really the crucial thing.
Yeah. So, exactly.
So what we are trying to do, I mean, you're right. Of course, if you leave complete freedom and you have lots of parameters, you can fit anything.
Yes. That's a good case.
So what we really try to do is we try to put a lot of discipline from the micro level, where we really try to see, okay, we cannot have a sensitivity in this particular decision rule, which is completely different from what on the micro level empirical studies have shown. So the way we try to deal with this is to put as much also empirical evidence and empirical foundation on the micro level that reduces the degrees of freedom that you have to reproduce those things on the macro level. And then if you are still able, although you put a lot of discipline, so to speak, on the micro level to capture those phenomena on different levels of aggregation, I would not necessarily claim that this is then the right model of the real world. But what I think is important is that this makes it very credible that we are capturing mechanisms that are relevant.
Right. And
I don't think we can even try to claim that we are capturing all mechanisms that are relevant, but we're trying to select the ones that seem to be important for these types of policies, and then we try to get at least those mechanisms right. I think that's as much as you can say.
Right. That makes sense, actually. When you talk to physicists, that's typically the approach they take, too.
Yeah.
All right. Well, then, yeah, thank you very much. This was fascinating for, I think, a lot of our audience. Yeah, thanks. Have a great evening.
Okay. Thanks a lot.
Okay, bye, guys.
So, wird noch aufgenommen, ne?
Okay. So, how do we do?
So, reden wir noch oder sind wir jetzt auch noch Pause?
Ja.
Aber ich glaube, wir werden noch aufgezeichnet.
Wir werden aufgeteilt. Okay. Ja, wir rufen die mal an.
Okay, also ich gehe raus aus dem Chat, ja?
Ja, okay.